Chapter 5, Torsion, Part B, Example 2, Parallel and Series Condition. If you remember this example, again, we have solved this example as well in a conventional method, which is developing a different equation. This is the previous video was about a axial force condition, a parallel condition, and this is a parallel condition in torsion. So again, if you look at the problem statement, two shafts embedded each other, and there is a torsional torque applied in a counterclockwise by the amount of T is 250 pound-feet, and the brass core and the steel outer has no way to rotate with each other with the same amount of angular of torsion or angle of twist. So that's a shaft shown in figure below, made from a steel tube which is bounded with a brass core. If a torsional torque of 250 applied at one end, free ends, as you can uh, observe here, a plot shear stress distribution. Now we are just going to calculate the forces here. So what is the share of a steel and what is the share of brass from of a torsional torque? If we do know the shearing rigidity of a steel is 11.4 10 cube ksi, and stiffness, rigidity modulus for brass is 5.2 10 cube ksi. Let's look at the conventional approach, which was the solution one. I will upload that video for you, the link for that video if you have not reviewed that. So that's again going through the bunch of equations, equilibrium equation at the beginning, then compatibility of displacement, then load displacement, connecting them, solving simultaneously of some of those equations, and finally get the result of torsional share for each material, which for a steel share of torsion is 242.6 and pound-feet, and for brass is 7.38 pound-feet in solution 1. Let's solve it in a far easier approach, which is again a hint because they have to rotate with each other. That's a reminder of parallel condition. So in this case, when two material are embedded in each other, it doesn't matter if it's in torsion or in axial load, that's a parallel because they have to behave at the same, like each other in terms of displacement. So let's see what can we have for parallel condition in terms of the share of the forces. First of all, from data, we we know uh, modulus rigidity for each material. We know R1 for steel, inner radius, outer radius for steel, radius for brass, which is all provided in data state problem statement. Length of shaft, which is provided in feet, and just that's a times 12 inches each feet, and that gives you a, let's put it 4 feet times 12 inches over feet, and gives you 48 inches because the units are in KSI, we are interested in inches. And torsional torque of 250 pound-feet applies. Let's first of all calculate the polar moment of inertia for each part for brass and steel. That's pi over 2 c squared. And if there is inner and outer, just subtract the two material, c to the power of 4. And again, and like then for solving the parallel condition, share of torsion for a steel is the stiffness of a steel over total stiffness times the torsional torque. So this is I call it torsional stiffness over over total stiffness. And just by having this and just replace this amount, but don't forget it to convert it to a inch because the units are in inch. So that's a 242. Mhm. And just do the same mass for BR and it just gives you a, or maybe do not need to, just double check the unit. I think that's a pound feet. But do the same for brass core, stiffness of torsional stiffness of brass, which if you remember, axial stiffness was EA over L, torsional stiffness is GJ over L. Hmm? This is axial. And that gives you a 7.30, 7.378. I think that's a pound feet, but double check the units for that. But they are the same numeric value from the previous method. Thank you.